Hello there, and welcome to Lecture 14. This brings us to yet another application of the integral, and this time our application is going to focus on statistics, and more specifically on probability. So we're going to start with the definition here. So my definition is for a random variable. So I have a random variable. It is in fact a variable, which takes on different values with specified probabilities. And that sounds very vague, but these variables could represent almost anything. And I'll show you a few examples in just a second. And even more specific here, we have that a continuous random variable takes on values from an interval of the real numbers. So for example, I could say, usually we write a random variable as capital X. So I'll say that the random variable here, what might be the height of a person, and that has to have some kind of units, so I would say inches. And when I mean that it can take on values from an interval, you have all the heights from, I guess, 0 inches all the way up to what a reasonable height would be for a human, I guess, if this was the random variable. So my interval would go from 0, and it would go up to some reasonable number, and it's every single height in between there. You could be any height between 0 and whatever the upper bound for that would be. And then another example might be the life of a toaster. That sounds like a novel that I need to write later in life. The life of a toaster. And again, you have to give these units so you can measure them. So this would be maybe in years. And the life of something isn't just like 1, 2, 3 years, right? It could be any interval, like 2.5 years or 2.222 years. So the life of a toaster, I guess, could be from 0 until, I don't know, 5, 6, 7 years, or any decimal in between. But the continuous random variables we're going to be looking at take on values in the interval. OK. So in general, a continuous random variable, then if you have one, then the probability that capital X, or whatever you're measuring, is between some A and B is given by, and we have notation for this. We have a capital P, stands for probability. And it's the probability that your capital X, the random variable, is between two values. This is equal to the integral from A to B, so the lower bound and the upper bound you're considering, of f of x dx. So this is kind of the application for us. We're going to use the integral to get the probability of certain intervals happening for a particular variable. And this f of x right here is a special function. We call it the probability density function. And I will very often abbreviate that PDF. So that those mean the same thing. So this lowercase f is called the PDF. And what it is it gives the relative likelihood that the random variable you're looking at takes on values near x. So it kind of measures how likely it is for that situation to occur. And every probability density function satisfies two properties which you need to know. So the first is that the probability density function is non-negative for all values of little x. So that's one of the properties. This is because probability should be 0 or positive. There's either a chance of something happening, which is like a positive chance, or there's no chance of something happening. But it doesn't make sense to have negative chance for something to happen, right? So that's why you have this. And then also, if you integrate from negative infinity to infinity, so you integrate over every possible thing that could happen, then that better equal, I'll put a dx right here, that should be 1. And that's true because the chance of anything happening, if you put all the possibilities together, that should be 100%, or 1. So 0 is the chance that it can't happen, and 1 is the chance that it's certain that it would happen, that it would definitely happen. Let's take a look at this example right here. So here my probability density function, the lowercase f, is given as this piecewise. And it has this function when x is non-negative, and it's 0 otherwise. And so this is a PDF for some random variable x. It could be really anything. I don't know, any kind of thing like the two things I named over here, but capital X is just going to represent something. We want to find the probability that this variable is between the values 1 and 2. So the probability that you're somewhere between 1 and 2. Well, to find the probability, you apply this formula. So what I do is I take the integral from the lower and the upper bound of the interval I'm considering, and it's of f of x dx. Now, on the interval 1 to 2, the piecewise function says you're talking about this up here, right? So from 1 to 2, I'm focused on integrating the upper part of this piecewise. So this is 2x e to the negative x squared. And now the problem just turns into going back to your integration techniques. Do you know how to integrate something like that? Well, I see a clever u sub I could do. So let's say u is the power. It's a very common thing to choose for u, is a complicated exponent. And then what would du be? That would be negative 2x dx. And if I rearrange that a little bit, like I do in class normally, I have negative 1 over 2 du is equal to x dx. So I know exactly what to substitute out here. So what I'm going to get then is integral of, I have e to the u right here. And then if I look at this, du substitutes out with this 2x dx. I just need to include a negative sign. So really, once I've done that entire substitution, all I'm left with is negative integral of e to the u du. Now, this is in terms of u, but I got to change the bounds, right? So that's what I'm going to do. Remember, this is x and this is x. If you plug in 1, you would get negative 1 for u. And if you plug in 2, you would get negative 4 for u. So I'm just changing my bounds. And then a negative in front of an integral flips the bounds. So you could say this is actually the integral from negative 4 to negative 1, and then get rid of that negative sign altogether, of e to the u du. Well, the integral of e to the u is just e to the u. So I have to, into my e to the u, I'm going to plug in negative 1 and negative 4. And then if I plug that in, I get 1 over e. Remember, if you plug in a negative power, it's 1 over it, minus, plug in the lower bounds, 1 over e to the 4th. And if you want an approximation of what that probability is, I calculated it to be 0.3496. So there's about a 35% chance that whatever the heck this thing is, it's between 1 and 2 at some given moment. When you're doing these problems, make sure you get an answer it's got to be between 0 and 1, right? If it's not, then you didn't compute a probability. There's either a 0% chance something happens, or it's a perfect 100% chance, or it's somewhere in between, right? So just do a sanity check when you're done. 35% actually is between these two numbers. So how about this one? So it says, for what value of k, so this k is a constant, is this probability density function from 0 to x to 4, and then it's 0 otherwise, so we're just concerned with this interval right here. For what value of k would this be a probability density function? Well, how would you figure that out? Go to our properties. Remember, if you integrate over every possible scenario, you're supposed to get 100%. That should be all the possibilities. So that should account for every probability and be 100%. So when we integrate over the entire thing, we need to make sure we get 1. That's got to be true for every PDF. So all right, that we need to figure out that this integral right here, the integral of kx 16 minus x squared to the 1/2, I just changed the root to a 1/2 power. So if you integrate this, and if you integrate it over the entire interval, you're supposed to get 1. This time, instead of negative infinity to infinity, the only values you care about are from 0 to 4, because otherwise the thing in here is 0. So if you integrate over the entire interval from 0 to 4, you're supposed to get 1. We need that to happen. So first what I'm going to do is I'm just going to go ahead and integrate this piece right here. I'll ignore the k, and I'm just going to try to figure out, okay, well, what's the integral from 0 to 4 of x 16 minus x squared to the 1/2 dx? What is that going to be? And the way I would do this is I would do a u sub. I'm going to say, well, u is going to be 16 minus x squared. And then my du would be negative 2x dx. I'm going to sub out this x dx. So that means negative 1 over 2 du. That's x dx. So I forgot to write x here. This is x dx. So then I'm going to continue. I'll continue over here. So I'll go down here. So x dx right here is the same thing as negative 1/2 du. And then this is u now to the 1/2 power. And then what would my new bounds be? Just like the last problem, I need to switch those out. So if x is 0, u would be 16. And if x is 4, u is actually 0. And remember, if there's a negative out front, you can flip these. So this is actually 1/2, change it to a positive, and then flip these, and it would be 0 to 16 of u to the 1/2 du. But integrating this is just doing the power rule backwards. So if you integrate that, it's just u to the 3/2. And then you would get the 2/3 in front. There's already a half here. So you need a 1/3. You can check that. Pause and check that if you need to. Take this, do the derivative, and you'll see that you'll end up with the 1/2 again. And then I've integrated now, so I can plug in 16 and 0. And now to plug in 16 into a 3/2 power, just follow me here. So if you plug in 16, always do the lower number first here, the denominator, because that's a square root. It's going to keep the number small. So you have 16, square root of 16 is 4, and then you do the numerator. 4 cubed is 64 over 3. Plugging in 0 to any powers is going to be 0. So this 64 over 3, I need that, because now I can go over here and solve this equation. We need to solve this. I know that if I factor out this k, bring that constant out, you can do that for integrals. What's left in here, 0 to 4 of that integral, I solved it. It's 64 over 3, and that has to equal 1. So how do you get 1 from this? You just flip this and move it to the other side. So actually, k is supposed to be 3 over 64 in this case. And what did we do? We found the k value now that satisfies condition 2. So we've made sure that this is a probability density function because it's going to integrate to 1 now. I've chosen the k that would do that. In the next part of this video, I'm going to show you 2 more definitions, and they are the mean and the median of a probability distribution. And we're also going to do more examples. So I'll see you in the next part. All right, welcome back. So let's do another example and then talk about 2 more definitions before we wrap up today. So here's our first example. It says gas is delivered to a gas station once a week. The amount of gas in thousands of gallons follows a distribution of capital X. That's our random variable. This X is going to represent the number of gallons of gas the station has in thousands of gallons. And it has a probability density function of f of x equals 5 times 1 minus x to the 4th. So that's true when x is positive if we have a positive amount of gallons. And the probability density function has weight 0 otherwise for negative values. The question is, how large does a tank need to be to ensure there's only a 1% chance that the station would run out of gas at any given time? So what I need then is we need the probability of, and I guess I would start with, I have 0 gallons of gas all the way up to some number b. So I need to have enough gas to ensure that 99% of the time I'm good. So I want the chance of this to be 99%. So if I'm good 99% of the time up until I have this amount of gas, then 1% of the time would be left over, right? And I wouldn't have had enough gas. So this is what my logic here is. We need to get b large enough so we're covered 99% of the time. So that's what we need. So how do we do the probability? Well, probability of from 0 gallons to b thousands of gallons is going to be the integral from 0. And this time I don't know the upper bound. I'm going to solve for it. So I'll just call it b. And then the probability is going to be, I'm going to integrate the density function, which is 5, 1 minus x to the 4th dx. And remember, I need this to be 0.99. I want to be good 99% of the time, so people aren't angry constantly at the gas station. So then I'm going to integrate this. That just involves taking this 4th power and making it the 5th power. So I have that 1 minus x to the 5th power. I go backwards. Now think, if you went forwards with this, you'd use the chain rule. You'd have 5 in front. The derivative of the inside gives you a -1. So actually going backwards, I need to put a negative sign here to account for that. And you can check that that's the integral because you then take the derivative. 5 goes here, and a -1 from the chain rule will cancel that, and you'll get back to where you started. So this is the integral of this. I need to evaluate this from b to 0. So let's plug in b. I'm just going to get -1 minus b to the 5th minus, and then we're going to plug in 0. So you get minus, and it's just going to be 1 in here. So I'm going to get -1. So that's what I got when I plugged in b. And when I plugged in 0, and remember, this has to be equal to 0.99. That's the whole point of this. This just gives you +1. So then if I subtract the 1 over here and multiply by this negative, I'm left with 1 minus b to the 5th is equal to 0.01. And remember, I'm solving for b. So I'll take the 5th root of both sides. So I'm going to get 1 minus b is, I'm going to say 0.01 is 1 over 100. To the 1/5 power, that's how I cancel this 5th power. And if I solve for b, if I just rearrange that, b is equal to 1 minus 1 over 100 to the 1/5 power. And I got a decimal approximation just to kind of show you what this would be about here. So this would be about 0.6018. Remember, this is in thousands of gallons. So if I move that decimal point over 3 spots for 1,000, that means I need about 602 gallons. That tank has to hold 602 gallons of gas. And then I would have the situation where I'm covered 99% of the time. OK, so you're solving for a different thing in this time. You're solving for one of the bounds. And the other problems we were solving for the actual probability. So now I've shown you a couple of examples of everything. Let's talk about these 2 final definitions. So there are 2 common measures of center of a probability distribution function. And they're called the mean and the median. So they are 2 specific formulas. So the first one is, let's say you have a PDF, and we're going to call it f of x. So just like we've been calling it. So say your PDF is little f of x, then the mean is given by little x times f of x dx. And you integrate over every possibility for x. The median, on the other hand, you have to find the lowercase m such that if you start from that spot and integrate everything else beyond, if you integrate the probability density function from that point on, you get exactly 50, or 50%. So if I can kind of maybe show you what this represents here. So let me go like that. So let's say we have this curve representing the probability density function. What the median would do, I'll start with that one. What the median would do, and maybe I've drawn that a little bit off. It's going to be kind of subjective. But what the median does is it finds the spot where you're exactly 50% in area. So like maybe somewhere like right here. This will be my little m. So that if you compare on the left and the right side, you have 50% of the total area on either side. And this is the median. So I'm going to say that this is 50-50. Or if you have taken stats before, this is the 50th percentile. It's that spot where the areas are equal on the other side. Now the mean, on the other hand, it's a weighted thing. So this is like, imagine I had this object, and I was trying to balance it on my finger. Or I could do it with like a pen. I'm not coordinated enough, so I can't actually do it. But the mean is the spot where the actual weights I can't do it, so I'm just going to give up. But like, imagine you're balancing this on your finger. If you could perfectly get it to balance on your finger, it's that spot where the weights are the same. So like, it's really chunky over here, right, on the left side. So you would have to move your finger pretty far to the left for this one because it's more weighted on the left side. So the mean is that spot where the weights are the same, okay? And if you're heavier on this side, then the mean's going to be more to the left. And if I could draw it a different way too, as well. Okay, so that's what we're looking for. So we're looking for like this moment where these two things occur. So let's take a look at this final example. We're going to calculate the mean and the median of this probability density function. And this represents the call wait times for one of our favorite activities is waiting or being on hold at a call center or whatever until we get help from customer service, maybe, or get transferred, I guess. But this, we're going to calculate basically the mean, the average time someone would wait, and also the time where 50% of people would wait longer than you and 50% of people would wait. So like right in the middle, basically, the median. So let's do it with this one. So these are just formulas. I've got them up here. The mean formula is the integral of, and I'm going to consider all the values, but I don't need to worry about negative values because time in minutes waiting on a call, that doesn't exist, right? So that wait's 0. But time starts at 0 here, just like it says, and then we would go to infinity. Hopefully you're not waiting infinity on hold. Then we need to integrate this function, but we also have to multiply by x. So we have x times. This 0.2 right here, that's kind of annoying. I'm going to change that to 1/5. And then this is e to the negative x over 5 dx. And we have to try to integrate this. So my thought is if I have two very different functions, I'm going to use integration by parts. It comes back to haunt us. So my choice for you is going to be the polynomial. It's going to be x, because that disappears. When I do my tabular method, that'll go away to 0. So that's great. For my dv, I'm going to take the other stuff. It's 1/5 e to the negative x over 5. If I integrate that once, I would get negative e to the negative x over 5. If you don't trust me, take the derivative of this. Go backwards. And I'll go one more time, and this is going to be positive 5 e to the negative x over 5. And my answer would be I would put plus here, minus here, alternate these signs, and it's these two diagonals multiplied together. So this is going to be equal to, I'm going to have to write a little smaller for this. This is going to be negative, let's see. So I have an improper integral, right? I have 0 to infinity. So I need to consider this as a limit. So I have the limit as t goes to infinity. And then this is going to be, I'm going to integrate this now. So I have x, and I have a negative here, so negative x e to the negative x over 5. And then I have minus 5 e to the negative x over 5. And I need to evaluate that from t to 0. So we're going to evaluate that from t to 0. I'm going to plug in t, so I get the limit. So x goes to infinity, or t goes to infinity. Plug in the t, I get negative t over e to the t over 5 minus, and if I plug in t here, I get 5 over e t over 5. So remember, these are negative powers, so they would go to the denominator. So that's what I get when I plug in t. And then minus, and if you plug in 0 here, if you plug in 0 for each of these, you get 0, and you get minus 5. So 0 here would be 0, and then this would be minus 5, equals, and I'm going to squeak this in. This is going to be really close. But as t goes to infinity, e grows way faster than t. So probably by L'Hopital's rule as well, you could check this. But this will go to 0 because the denominator grows way faster. And here I have a constant 5. And then this is going to infinity in the denominator. This is also 0. So this is just 5 minutes. Remember, the thing we were looking for was call time, right? So the average amount of time that you could expect to be on hold with this company is 5 minutes. That in itself is incredible. I've never been on hold for just 5 minutes. So, and if I was, I got transferred very promptly. So that's pretty good. So this is the moment in time where it would balance out perfectly based on my picture. Let's find the median. So this is the time now that like 50% of people would wait more than you, and 50% of people would wait less time than you would. So this one is we need the lowercase m such that the integral from m to infinity, of f of x, no x in front this time. The mean has the x in front of it, but median just has f of x. So f of x is 1/5 e to the negative x over 5. We need the time that's going to be equal to 1/2. This is easier to integrate. I don't need integration by parts. I can just do basically the first integration I did over here. So the integral of this equal to the limit as t goes to infinity. The integral of this, like I just said, is going to be negative e to the negative x over 5. And I'm going to evaluate that from t to lowercase m. So let's do that. This is the limit as t goes to infinity. And if I plug in t, I'm going to get negative 1 over e to the t over 5. Remember that negative power moves to the denominator. Minus, and you plug in m, and I'm going to get minus 1 over e m over 5. So I plugged in t, I plugged in m. Now, as t goes to infinity, again, this I have a fixed 1 over something that goes to infinity. That piece goes to 0. And here I get a double negative. I get 1 over e to the m over 5. And this needs to be equal to, we need that to be equal to 1/2. That's the whole point of being the median. So look at these. I could flip both of them, right? Two fractions are equal to each other. You can flip them. That's a trick. And I'm going to get em over 5 equals 2. Flip both of these. Use ln on both sides to solve for this. So I have m over 5 is ln of 2. And then multiply both sides by 5, and you have your answer. So this is 5 ln of 2. If you're curious about what that is, I got about 3.466 minutes. OK, so that wraps up this example. As always, send me any questions if you have them, and have a nice day. I'll see you in the next video.